Okay, welcome back, everyone. So, yes, I'm back. I know it's been quite a while, and yes, I have my standard excuses. Well, uh, school, of course, math classes, finals. But now, we've kind of settled in to summer, and so I think I'm ready to continue uploading. Um, I have a bunch of new math under my belt. It's kind of overwhelming to make videos when there's so many options and so little time. So that's why I've kind of been putting this off for some time. But I'm back, and kind of to just settle back into the YouTube setting. I have two little um, geometry problems for you today. Um, and the first one here, both of which are from the Norway Oval 2010. First one here is part 1A, and it reads, the point P lies on the edge AB, this edge, on the quadrilateral, I can't speak. It's almost 12 midnight, so I might explain it. Quadrilateral ABC, right? The angles BAD, right here, ABC, and CPD are all right, as we noted here, and AB equals BC. Okay, show that BC equals BP or AD equals BP. So I kind of gave you guys a little picture of what's going on here. I don't think this is very difficult to arrive at. I just didn't want to do it on camera because, well, my drawing skills are not optimal, as you see. And so I didn't want to waste time doing that. But why don't we just get started? Well, what I did first was I started to do a little bit of angle chasing, and to motivate that, well, these two triangles look like they're similar, so we kind of want to prove that real quick. And to do so, we proceed with angle chasing. That's how I call it. I really don't know if this is a rigorous way of calling it. Anyway, let's start off here. So let's note this angle with a single line. We'll then notice that this angle here is complementary to this angle. Indeed, this is a right triangle. The angles add up to 180, and hence these two angles must add up to 90, subtracting that 90 off. But following that argument, notice that these three angles are supplementary. They also add up to 180. And therefore, using the fact that this angle is also a right triangle, it follows that this angle and this angle are also complementary, and so this angle is just equivalent to this angle. And so following a similar argument, we're going to get that this angle is just this angle. Okay. I wonder how many times I just said this angle there. Okay. Well, what does this tell us? Well, notice that we have three congruent angles in both of these triangles. All three angles are the same. And therefore, this tells us that this proves that these two triangles are similar to one another. So let's just note down some lengths so that we can use this fact. We say this is A, this is B, this is X, this is Y, okay? Then we can sort of match the angles together. We think about this angle matching this angle, we would rotate this counterclockwise by 90 degrees. And so we'll have A corresponds to Y and X corresponds to B. Namely, A over Y, using similarity, A over Y is equal to X over B, or cross multiplying. This implies that perhaps I'll be conservative with space. A over Y equals X over B. Therefore, we have that AB is equal to XY. This will prove very useful in conjunction with what we're already given, namely that AB equals BC, which can quickly be rewritten as X plus Y. Notice that AB is just X plus Y. We strategically chose those variables. Right, and then BC, well, that's nothing but B, and AD is A. So let's just rewrite that as A plus B. So this is useful. I'll write that over here. X plus 5 is A plus B. So now when we analyze this, what we're trying to prove here, and actually I'll rewrite this a bit, BC is Y, BP, or BC, that's B, BP is Y, AD is A. Okay, so we've rewritten our goal that this OR kind of motivates us to find some expression which we're able to factor so that we get two different solutions with zero product property. Those correspond to this using these two equations, and that motivates our next step, which is to square both sides of this equation, which is further bolstered by the fact that, well, we were given this equation, and so a lot cancel. Well, one major term cancels, which is the resulting 2xy and 2ab as a result of the square. And so that will give us some interesting information. It's always good when it comes to problems to make sure you're using all the information you're given. So that's always useful. And so once we square this, squaring gives us x squared, and after all the cancellation, which is a result of this equation, x squared plus y squared equals a squared plus b squared. Or if we move a squared and b squared to both sides to this side and rearrange terms a bit, we have a squared minus x squared minus a squared plus y squared minus b squared, which is 0. Right? Okay, well, how does this help us? Well, notice this difference of squares. And since we're trying to factor this, it's pretty natural that we're going to apply the difference of squares formula. And furthermore, we will want to apply perhaps this original equation that's given in the problem to maybe factor something out. So let's try that. Perhaps if I use the space that I have, that would be a good idea. So let's apply this difference of squares. We have x plus a, x minus a, plus y plus b, y minus b equals 0. And so in searching for something to factor out, we go back to this equation here, x plus y equals a minus b. And we notice that, well, x minus b and y minus b are quite related. In fact, if we try to solve for x minus a using this equation, we actually get that x minus a is equal to b minus y. It's just some basic algebraic manipulation. And well, what is that? That is simply y negative y minus b. And so we can freely factor out this y minus b term. And with a bit of manipulation, we'll end up with y minus b times this sort of ugly factor. But this actually ends up simplifying nicely, as we'll see. So we're left with y plus b minus this entire term, x minus a, since we're left with this minus factor equal to 0. In other words, this splits up into two parts. Y equals b, which is one of the desired results, or y plus b minus x minus a is equal to 0. Okay. Well, let's see. We want to manipulate this equation so that we get the desired result. We finish the desired result, which is a equals y. How do we do that? Well, we leave the y minus a and manipulate this b minus x term, once again using this original equation given in the problem statement. So, well, notice that b minus x is nothing but y minus a. And so we can actually combine these two terms, giving 2 times y minus a is equal to 0. We're canceling the 2. We finally get our result, y equals a. And so, in summary, we have indeed found that y equals b or y equals a, but notice that this is exactly what we're trying to find, just rewritten with our defined lengths. So I'll just clear the board and let's just take a look at the next problem. Okay, so here's the next problem. Well, we're given this square, and within this square there is a red area, a red region, which we are asked to find the area of. And we're given that this square has length 1, and that these parts are equal to a, where a is on the interval 0 to 1, closed interval 0 to 1. Okay? And we are asked to find the area of this red region in terms of a. Okay. Well, there's quite a few ways of doing this. In fact, there's a way to do this with calculus, I believe. Post your solutions in the comments if you find a way to do this with calculus. But the way I did this problem, the first way I did this problem was as so. It's not that elegant. I couldn't really find a way to do this without some involvement of coordinates, so please let me know if you have a more elegant solution without coordinates. I know coordinates can sometimes mask the elegance of a problem, the elegance of a geometry problem. But anyway, let's jump into the first solution. They're happily related though. Anyway, we'll start by splitting this region up into parts. And again, this is nowhere near a perfect square, but we have to work with. You're gonna have to work with my drawing abilities. So we're gonna split this up into parts. We're gonna construct this line segment, and also this line segment. Okay. As such. And well, what are we doing? Well, the idea here is that we're splitting this region, this entire square into parts that we can find the area of. And then we can subtract off the area of these parts from the area of the square. And then we can show that, well, in showing that these two triangles are congruent, we can just divide that result by 2. Okay? Well, let's argue why these guys are congruent. Well, notice that both of these, we're kind of thinking about coordinate systems, but it's not necessarily necessary. Both of these lines, we're putting in on these two lines. To do so, indeed, we're showing that all sides are congruent, all sides are equal, and hence the triangles are congruent. This line passes through, both lines pass through this point, and they also go to the edge of the square. So by symmetry, these two lengths are the same. Indeed, this is a 45-degree angle, so we can think of this line as being symmetric, right? So that's why we can argue that. And by symmetry, we can apply the same argument to say that these two sides are equivalent. Okay? And in fact, these two sides are equal, right? So this is indeed an isosceles triangle, okay? And furthermore, these triangles pretty obviously share this one side up here. And so, indeed, all of the side lengths are equal, and hence these triangles are congruent. So, if we extend this area, this red area, all out to this triangle, and focus on the outer edges, we'll be able to solve the problem pretty nicely. Okay, let's see what we have here. You can do this multiple ways. You can split this up multiple ways. This is how I do it. Well, first of all, we're kind of interested in this intersection point. But to find this, the only way I could think of is using coordinates, where we have this point here is the origin. And then in that case, this line is given by y equals x. Quite obviously, and this is a 45-degree angle, right? Bisects this right angle. And the equation for this line here, well, let's see, it goes a in the x direction and 1 in the y direction. So, and it's a negative slope, so we're going to have 1 over a, change in y over change in x. Y equals 1 over a, minus 1 over ax, plus, well, the y-intercept is just 1, right? Okay, so to find the intersection, let's just set them equal to one another. Or more precisely, let's just plug in x, let's just plug in y for x. So we're just going to have y just directly adding this 1 over a y on both sides. And then factoring in y, we're going to have 1 plus 1 over a equals 1. If we get a common denominator, we're going to end up with a plus 1 over a. And if we take the reciprocal on both sides of that, divided by on both sides, that is, we have y equals a over a plus 1. So in other words, using the fact that this is y equals x, this point is actually just a plus 1, a plus 1. And in other words, if we clear all this out, just pretend we never used the coordinate system. Let's be a bit cheeky here. Just say we never used the coordinate system. It'll never get you. You just say that, right? In other words, that length there is a over a plus 1. And since this is line by symmetry, this length here is also a over a plus 1. But we won't be needing that in this first proof. Okay. Well, now let's hone in on this triangle here. Notice that this is a height for this triangle, right? Assuming that the base is down here. But notice that the base is nothing but 1 minus a. Given that this side length is equal to a, we're just subtracting a from this general side length 1. And in other words, we can calculate the area of that triangle. But notice that, let's be a bit smart here. And since these sides are pretty obvious, these things are pretty obviously congruent, so their areas, namely their areas, are the same. We're not going to worry about the 1/2 for now. So, in other words, we're just focusing on the area of all of these things at the moment. So we'll call that A star. A star is equal to, well, 1 minus a times the height, which is a over a plus 1. Right. And so, furthermore, let's look at this part. Well, that's just a nice right triangle. We know the base is a, and the height is quite obviously 1. And so that's just going to be plus a, ignoring the 1/2. Well, that's pretty nice. We're actually just going to be left with, in that case, if we, well, there's a few ways of simplifying this. Let's just kind of, in order to find the area of this red triangle, we're going to need to take a star we're going to need to take a star, subtract it from 1, and take half of that. Because once we subtract, we're going to be left with both of these, which are congruent. And so if we take half the area, we're going to get the desired area. So 1/2, 1 minus a star, which is just this. So 1 minus a over a plus 1 minus a. So if we combine these two terms, this is going to be equal to 1/2, 1 minus a minus 1 minus a times a over a plus 1. So factoring out the 1 minus a gives 1/2 times, or I'll just write 1 minus a over 2 times 1 minus a over a plus 1. And well, notice that this term is nothing but, well, that's just going to be 1 over a plus 1. And so, all in all, we're just left with this is equal to 1 minus a over 2a plus 2. And that is the first solution to this problem. I'm going to clear the board and look at a second solution. Okay, so let's jump into the second solution. For this solution, we're going to start by constructing another diagonal here that runs through, well, runs through this red area, this red region. Trying my best to construct it. And if this was a perfect square, this here would be a right angle. Indeed, if you think of these as lines, they're orthogonal to one another, right? So their slope is indeed negative. They're reciprocal. And so this has to be a right angle, right? And well, that is, in other words, this this length here is a height for this red region, this red triangle. And well, what is this height? Well, notice that by symmetry, these intersect at exactly half this length. In other words, well, there are a few ways of calculating it in that case. How I would do it is I would just simply take half of this general length, which we know is root 2, using Pythagorean theorem if you'd like, or just basic rules of 45, 45, 90 triangles, right? So in other words, this length is just root 2 over 2, half of that length. Okay, so that's the height of our triangle. How do we find our base? Try to draw that nicely. Well, notice that I rewrote this coordinate here as if we have a coordinate system. We don't really have it in place right now, but I just wanted to write that out so it's clear. But notice that to get this base, well, we already know the length of this full line segment. I can't draw it. That's just going to be root 2. So if we can subtract off the lengths of these pieces, we can get that base. And well, it suffices to calculate the length of one of those, as the other one is just equivalent by symmetry, right? And so to do that, well, we use these coordinates. Notice that this distance, since this is our symmetric, since this line is y represented by y equals x, that's one way of looking at it. There's other symmetry arguments to look at. But both of these lengths are a plus 1. Now, let me put it this way. If we look at an isosceles triangle, and notice that it's isosceles because both these lengths here are a plus 1. Using this result here, this intersection, well, this is a right triangle, and so these angles are 45, 45, and therefore this side is root 2 times a over a plus 1. And therefore, our base is nothing but root 2, which is the full length, subtracted from 2 times this little length here. which is 2 times root 2 times a over a plus 1. So, in other words, this is what we're left with for our base. And therefore, we can just directly calculate the area of the rectangle. It's kind of nice, right? And therefore, we just get 1/2 base times height. For base, I guess I should write it like this. If we were to factor out root 2 here, perhaps I'll just do that directly. 1 minus 2a over a plus 1. Okay, and so 1/2 base times height. Our height is root 2 over 2. If we bring that root 2 out, we're going to get root 2 squared, which is this 2. So that 1/2, that half is canceled with that 2, and we're just left with the 1/2 beforehand. And so, in other words, we're just left with this final expression, which is nothing but 1/2. We just get common denominator, 1 minus a over a plus 1, which is what we got for the last solution. Same thing, 1 over a plus 2. So I thought it was kind of nice to look at two fairly different solutions and notice that we got the same answer. It's always a good way to check your answer. So I think that's a pretty good way to end this video, and I'll see you next time. Hopefully something a bit more well prepared. See you then.